All right, hello, welcome to this week's Off by One security stream. We got a special guest visitor here who's been on before, Jonathan Reiter. He came on previously and talked to us a bit about how to go about looking at building custom implants, since so many things get detected out of the box these days. It's an important skill to have as a red teamer. So he does a lot of work in the kernel space and such. And so when thinking about this topic here that I'm covering this week, I thought, hey, would it be great if Jonathan could come on? And thankfully he was able to do that. So thank you, sir. Appreciate it. I think most of you know that Jonathan is the author of the SANS Sec 670 course, which is all about writing custom implants. So this specific stream that we're going to do here spawned out of something we looked at last week, which was last week I was looking at the mitigation that's part of exploit guard on Windows, which is do not allow child processes. And that is known as the calc killer, because a lot of shell code, when people would write proof of concept, would spawn a calculator. Well, this would prevent that from happening. So I had a little program that I created called create process. And when you run it without exploit guard, specifically the do not allow child processes mitigation turned on, it worked fine. It launched a calculator. When you turn on the mitigation, the calculator did not spawn anymore. So I wanted to understand how that mitigation worked, because a lot of the mitigations in what was EMIT, the Enhanced Mitigation Experience Toolkit, which is now exploit guard, a lot of those mitigations are user mode implemented, meaning that there's lots of hooks on things like the import address table, where when you go to call a critical function like virtual alloc, it goes and validates things like, is the stack pointer at the right location? Or is the destination where we're changing permissions in an area that it shouldn't be, like the stack? So this specific mitigation, when I first took a look at it, I was like, oh, it doesn't seem to be anything going on in userland. So of course I jumped into the kernel and set a breakpoint initially on the create process function. And then I went and executed from a command shell the create process application, which is supposed to pop a calculator, and we hit the breakpoint. We started to go in and look at kind of how this mitigation might work. And we looked inside the Windows kernel itself, the NTOS kernel with IDA Pro, and we found a bunch of mitigations, functions with names which looked like mitigation names. So it made it pretty easy to find what we wanted to look at and then to start doing some reversing. So specifically, let me go over to a different IDA Pro instance here and look at something. So this right here that I'm in currently is not where I want to be. What are we in here? We are in the PS convert to GUI thread. Oh, the reason I'm in here is because another mitigation I wanted to look at was the one that prevents applications from being able to access the Win32k syscall table. And in order to do that, if you're a GUI thread, so there's non-GUI and there's GUI threads, you need to see like, well, which one should be able to access the Win32k syscall table and which one should not be able to. And so if you turn that mitigation on, it prevents you from being able to access the Win32k syscall table, which has over 1,000 accessible APIs. So most programs just need to go through the NT syscall table. So basically it's a mitigation where if you know for sure that the application that you want to protect does not need to access the Win32k syscall table, so it's not a GUI thread, then you can turn that mitigation on. And I realized it was another kernel enforced mitigation, so that's why I end up here. I went ahead and we're not going to really talk about this one, but I went in and did a bunch of documentation so far. Notice some things like it's checking previous mode, which is pretty normal. I'm sure you've heard of previous mode before if you've done any kernel exploitation. I had Connor McGar on a couple months back, and we specifically looked at the technique where you can set the flag or modify the flag. It's just a little flag, and it's either on or off. It's just a 1 or a 0. And it's a way to let whatever process you're currently in or context you're in, it lets it know whether or not the code is in userland or kernel land. So are we executing under the context of the kernel or userland? Because if we're in the context of the kernel, we should never be executing userland code. So that flag there allows you to set that. Now, what we learned in the past, up until really recently, like late last year, is that you could easily flip the flag in previous mode and you could get a write primitive that way pretty easily. And they protected that. They started protecting that recently. And so there are other ways to go about getting read-write primitives in the kernel, but they take away our techniques more and more. So the reason I talked about previous mode there is just because that's what's happening here. We're getting K-thread and we're looking at the offset as to where previous mode is, and we're checking to see if it's on or off. Down here, we're loading thread flags member in. We're seeing if any flags are set. Down here, we're loading the eProcess address from the KAPC state, and then we're loading the mitigation flags field from eProcess into the accumulator register. We're copying it, and we're checking the disallow Win32k system calls flag. Now, there's a couple of different things going on here in the token. There's a mitigations flag member, and that one got eaten up to where they created a mitigation flags 2 member, which is a newer one that supports things like shadow stacks would be an example of a flag that would be set in there. A lot of those mitigations, as you've heard me say previously, they are not on by default. Still today, even in Windows 11, they're not on by default because then this goes back all the way to Service Pack 2 on Windows XP. If Microsoft were to turn all these mitigations on by default, a couple things could happen. One is it could break your applications, especially homegrown applications. 2, there is overhead associated with it. Anytime we're turning on mitigations, that means there's code executing to do some validation of some sort, which is going to have associated overhead. So the question is, how much overhead? And I'll give you an example. When you think about a solid mitigation like stack canaries or security cookies, Windows calls them, that's a great mitigation because we can protect variables on the stack, we can protect a return pointer and other things. And it ends up being a inexpensive, so not a lot of overhead mitigation, because basically it says upon function prolog, when we're setting up the stack, push the canary onto the stack, and Windows actually XORs the canary that is randomly generated once per process. It XORs it against the base pointer to give it even some more randomness. And then when you go to when you're epilogue, so you're about to leave the function and return back to the caller, before you hit the epilogue code, it validates that the canary is intact. It's not been modified or corrupt. That is an example of an inexpensive mitigation because it's just a couple lines of code and it's a perfect time to go and do that validation versus heap cookies. Windows or Microsoft implemented heap cookies, the first attempt at it, all the way back on XP Service Pack 2. And what they found is that every chunk, so a chunk is basically a memory allocation on the heap, we call it a chunk, and it has metadata associated with it. So every chunk that's allocated, there's metadata on the front of it. And there was a 1 byte field in the metadata that they realized was not needed. So they used that 1 byte field in the header as an opportunity to implement a heap cookie or heap canary. Couple problems there. One is it's only 8 bits. So that's not good entropy, right? We have a 1 in 256 chance of guessing what the canary value would be. The bigger problem, though, is when do we check those canaries? With the function prolog, with stack canaries, that makes sense. We do not allow execution to return to the caller until we validate that the canary is intact. That's an easy one. But on the heap, we might have thousands and thousands of chunks allocated at any moment in time. When is a good time to go validate those flags in the chunk header? We can't do it every prolog. That would be a ton of overhead to go and check all the chunks that are allocated to make sure that the field is intact. So maybe we check it just during allocation or deletion. And then when you get to the low fragmentation heap, which pretty much went into full effect on Windows Vista, and it's still there today. We have segment heap and we have low fragmentation heap in the kernel now. It's turned on by default. There's no waiting for 18 consecutive allocations like there used to be. But the whole point of a front-end allocator is that there's a rule on the heap with most operating systems and most heap allocators is that no two free chunks are allowed to be side by side and free. We want to reduce fragmentation, so we coalesce or merge freed chunks that are neighbors. And so that's great. That's something we should do. We should optimize things all the time, but there's overhead associated with that. So the front end allocator that says, well, let's service memory allocation requests that are commonly used. So for example, if you look at something like a browser, you have common HTML elements like a span, a div, a button, and those objects have a static size associated with them, always the same size. So when you call heap alloc to create that object or the memory for that object, the size is static. So if we're dealing with something like a browser, there's a lot of HTML elements that are always going to be used. So it makes sense to have the front end allocator service that, because we don't care about fragmentation if it's something that's going to constantly be used. So that's one example of why we have a front end allocator and a back end allocator. So the reason I went through that is just to give a little context, but specifically, that is when I saw a blue screen pop up on Jonathan's box there. That's funny. That is when the heap cookie or canary effectively went from 1 byte or 8 bits to being 32 bits or 4 bytes. Because in the structure associated with the LFH heap structure, there's the equivalent of a canary. And that canary is XORed against the first 32 bits of every chunk header that's serviced by LFH. So it effectively acts as a security cookie or canary. But the question still remains, which is, when do we go about checking that? We can't check it every time we do a ret because the overhead would be significant. So I know I went on a little tangent there, but I don't like to high level say something and not go into add any context. So the reason I brought all that up is because Microsoft doesn't turn all the mitigations on because 1, it could break things, and 2, the overhead. And I just gave you a good example of something that would cause significant overhead if we were to do that. So as time goes on, like originally, data execution prevention was not on by default on Windows XP Service Pack 2. Well, it was on by default, but only for Windows services and processes that Microsoft knew could deal with DEP. But Microsoft didn't know all the other applications made by third parties or even your own organization. Can they support DEP? You should not need code execution on the stack or the heap. So the execute permission should never need to be turned on. But there are bad applications that sometimes needed that, or there might be some stub areas and stuff that needed that. So after enough time went by, Microsoft decided, I think application development and such is mature enough to where we can turn this mitigation on by default for everything. And then if you want to turn it off for a specific application that you know would be negatively impacted, you can create that exceptions list. So the point being, as time goes on and Microsoft feels more comfortable about turning these mitigations on by default because it shouldn't break your applications, they start switching those things on. Microsoft would kind of be in a bad position if you think about it, because people will complain, why isn't this mitigation on by default? And they would say, because it might break your applications, and then you'll be mad at us. And then they say, well, okay, if they don't turn it on by default, it's why don't you turn them on? If they turn everything on by default, hey, Microsoft, you broke my application. So they're kind of stuck, right, in an unwinnable situation. So they wait till a certain amount of time goes by where they feel like it makes sense to turn that mitigation on by default, which gets us to today. These mitigations that we look at in Exploit Guard are not on by default for the most case because there's a good chance it will break things. For example, shadow stacks. Shadow stacks is a relatively new mitigation, not a new concept, but a new mitigation that says each time we execute the call instruction, we push the return pointer onto the stack. Let's make a copy of that return pointer and put it onto a hardware protected shadow stack so that if somebody overwrites the return pointer via a buffer overflow, that return pointer overwrite that you did won't match what's expected on the shadow stack. So the reason they don't turn that on by default it's actually less about it'll break your applications, more about does the architecture that you have on your laptop or system support it? Like on Intel, it wasn't until the Tiger Lake CPU that shadow stacks was enforceable. So Intel had to enable that. So until we're at a point where everybody refreshes all their hardware and 99% of systems can support shadow stacks, they're going to leave that off, I would imagine. Because if they turn it on, it'll break things. I don't know exactly what happens. And there's other ones as well. So I'll just give you an example of a couple there. So we are looking at the newer mitigations. As an attacker, I remember Microsoft said a long time ago when the Enhanced Mitigation Experience Toolkit was out, EMIT, which came out with the release of Windows 7, there was about a 5% adoption rate, which means that hardly anybody was using it, which is sad because they're putting a lot of time and effort into that toolkit. And I remember too, Microsoft did this article one time, it was on Channel 9 or something, whatever that thing is called. And they said that when they go and test their applications and their services and features and updates and all that, they do it on a fully patched system. So what's the definition of a fully patched system? You would think it means all patches are applied. But a lot of organizations and admins will say, we are patched up to date, up all the way to this month's Patch Tuesday. But in fact, there's a bunch of holes because they may have deferred patches to certain things because they were afraid it was going to break something. So a lot of times it's like Swiss cheese where there's a bunch of holes and you are patched up to date with some patches, but not completely. So we'll talk more about that and stuff and why it's relevant here coming up in a bit. But let's move into what we're going to focus on in this session. And that is, how do we document something that's undocumented? There's a lot of things that are called native. We call them native services, native APIs. Some people would refer to NTDLL as being native because it's not documented centrally by Microsoft, all the functions and such in there. Like what you're supposed to do when you want to call a function, maybe it's like a write to file function. Like you want to write to a file. Well, in order to write to a file, you've got to cross a trust boundary. You're going from software to hardware. That's an example of a trust boundary. So there's got to be protections and controls in place. So Microsoft would want you to call the function that you're supposed to call from the DLL that they provide to you to be able to open that up from the file system. What some developers will do, though, is they'll skip and go straight to something like NTDLL and call the NT equivalent of that function. The problem with that is a lot of times the arguments list and those native APIs and such that are exposed are not documented. So the arguments are not documented. So you may call a function that you're supposed to call, and it only wants 3 arguments. It wants a file name that you want to open. It wants, I don't know, a couple other fields, the permissions maybe. So you're supposed to pass it that. But when you get into the core function that makes the system call into the kernel, maybe that has 7 arguments. And you're like, well, what's the other 4 arguments? They're not documented. Well, what if I just put 0, 0, 0, 0? Yeah, it might work, but what are you zeroing out? Those flags probably mean something, but it's undocumented. So until somebody documents that, which could be you or somebody out there on the internet, it's a bit of unknown at that point, because then it goes into the kernel, and then something called the security reference monitor and such going to come in. It's going to look at your token. Tokens are very important, and that's why we're focusing so much on it. Inside the tokens are your privileges list, as well as these different flags fields that specify which mitigations are on or off or supported and such. So if the permissions and everything looks okay and you're allowed to do what you're requesting, then it's going to do a little calculation. There's something called the model specific register that always points to something. We've got things like the kernel processor region control block, and these are massive structures in the kernel that stores tons of information, and there's a million pointers pointing all over the place to various nested structures and different things. So it does some calculations, looks up in a dispatch table, determines what the address is of the function you're supposed to be calling, and then it performs what you've requested. But if you didn't know what flags to set for those arguments, then you could be introducing a problem yourself. So I think I missed a question here. Someone said, why did you choose Windows? It's so easy to hack. Well, Windows actually, I mean, to be fair, Windows has come such a long way. It is very, very secure compared to what it used to be. The things that Microsoft has done and is doing is something most organizations wish they could get to. It is very hard now to exploit kernel vulnerabilities and such. Occasionally there's something that pops up that's easy, but for the most part, the low-hanging fruit is gone. And there's so many default mitigations, aside from the ones that we're talking about here, that are in your way. This different virtualization-based security makes things difficult. Like, and most people, when you ask, they don't know things like, what's a low box token? I would say 99.9% of people don't know what a low box token is, because why do you care what a low box token is? Well, that has to do with, I can't remember the old, what was the old, do you remember, Jonathan, the old API you would call to generate a token that was going into like a sandbox, and you want to limit what it's capable of doing? I forget the name of it.
No.
Yeah, so that's fine. But you create something like a low box token, and you get into a problem. I think Project Zero at Google did an interesting article one time about privilege escalation due to the way low box tokens were being created, and the references that you need to kernel objects. You need to be able to do certain things. Well, it's almost like when you, on Linux, when you use chroot, and you change the root of the file system from the perspective of the application. Well, if you don't put all the dependencies into that chrooted area and where they're supposed to be, it breaks things. That's not a sandbox, of course, but that's just an easy analogy. So if you are putting something into a container on Windows and it's unable to do things it needs to be able to do, you run into issues. And I think what Google Project Zero found is that if you keep handles open in a low box token environment, then the process is deleted, but it's still there. It's like, if you look at the AP links, that process is gone, but it actually is still there. And there was some interesting privilege escalation that you'd be able to do. No, not a classifier token. I can't remember. I'll look it up though and mention it when Jonathan's talking in a bit. I've been eating up all the airtime trying to like get us to the point where we are at. So let me get moving on this. Okay, so what were we going to look at? I'm going to right now go in and set a breakpoint on the function that checks to see if the flag is on for child process being created or not. So let's go over to the debugger here. I'm going to go ahead and break. I still got some breakpoints set from the last time. So we do a breakpoint list. And I'm going to I'll just enable 0 and 2. So 2 is the one I really care about. That's the SC, which is a security reference monitor prefix. Token get no child process restricted. So breakpoint enable 0 and 2. And then we'll just say go. We'll go over to this guy, and I'm going to, oh, it's already hit a breakpoint. That's the thing. Processes, even if you're not doing anything on Windows, are being created constantly. Oh, it did it again. You're killing me. Come on. You know, I can just, if it just keeps breaking, I can just show it for whatever it's. Okay. Let me, wow, it is being painful right now. Let me kill the breakpoints for a second. Breakpoint disable. All right, go. And let me get over to the command shell that I wanted to get to so I can actually show you something. All right, here we are. Now, this is a regular command shell. So I'm going to go back over here. We're going to tell it to go with the breakpoint set. And I hope it lets me do this real quick. I have no idea why there are so many processes being created right now. It's killing me. All I need to be able to do is hit enter Give me a moment, please. Unbelievable. I have no idea what's going on, so I won't be able to show you what I wanted to show you, sadly, because it's doing crazy things. So let's go ahead and see what it's doing here. We're on NT create user process. Let's hit that breakpoint on get no child process restricted. So here we are. Let me set a, is that visible for everybody? Hopefully you're able to see that. How's it look, Jonathan? Can you see it okay?
Yeah, it's good.
Jonathan? Okay, cool, thanks. So I'm going to go ahead and say unassemble the function. And there's the whole function disassembled here. Now, this is actually going to be easier to show you in IDA. So let's go over to IDA. All right. And the function that we want to disassemble here is sc token get no child. All right, here it is. All right, we're now in that function. Let me zoom in. And what we're going to do, this is what we went over last week. We got the K-thread address and we lock it down. And then down here, we do these shifts and ands. So these shifts, what I've got highlighted here, are actually moving the flag that we want to check into the right position so that we can then do an and against it, because we're trying to check to see if the flag is on or not. And then we saw in the other function, which was the set version of this, it actually does a bit set instruction to turn that bit on. This is the one that just checks the bit. So we're shifting and doing it that way. Now, when we do these checks, if we go and look at the token now, of whatever we're playing right now, I'm just going to say bang process to see what process we're in. And we are in SVC host, so one instance of SVC host. So we'll now say bang token. This kernel debug session is going painfully slow. We are debugging the Windows kernel. All right, so I'm going to go bang token. And what we'll see in here is the token flags field. So right there, token flags, it's set 0x2000. So likely there's just one flag set on this one. This is not the token we're interested in, though. But also we can see the privileges above. For example, if we look at the process for cmd.exe, wait for this one to come up. What we'll see, if we were to look at this token, you would see that the privileges list is very minimal. But if we change it to an administrative one, then the privileges list would be much greater. So we saw in the code here in IDA, specifically if we look at the pseudocode, you can see that, let me turn, I got this old box here. Let me system that's in the middle and see closer on this Windows 10 box. All right, that should be better for you all. Now, right here, it's easier to read, right? Because it's saying, I renamed this stuff. So where it says token flags, I renamed that so that we know what we're looking at. But that's where it's checking the flags, and it's doing an and specific flag. This is what we're talking about now. This is the point of the webcast or stream, is those fields right there, those flags where it says 80000 or 100000 or 200000. Those are specific flags that are not documented anywhere that we've seen. And we thought, well, how many token flags are there? We determined there's 32 bits available. So 32 flags available within this field, starting with bit 1 and working our way up. What are all the flags? So that's where Jonathan and I got started on this. And I said, hey, I might have tweeted it out even. I said, does anyone have a reference to a document that shows you what all these flags are? There are other fields where Microsoft happily documents what all the bits are, but this one not so much. So I'm going to pass it over to Jonathan now finally, and we'll share his system so he can kind of show you one of the approaches that we took to go and figure this out. So give me a moment here. Take mine off and put Jonathan's on. Cool, there we go.
Sweet, looks good. Cool. All right. So thanks, Steve. Yeah. So when you hit me up with that message, like, what's up with these token flags? Do I have any notes or research notes or anything that might help you understand token flags and the bits for all that? And I was like, I have a little bit, but I don't have a lot that is confirmed or nothing that's really concrete. So what I like to do, my methodology is sometimes I'll check out the documentation on MSDN. Cool, but a lot of times MSDN docs can be not so accurate to say the least. So I like to go to header files. So what I did on my Windows 10 VM is initially I didn't know what header file I really needed to dive into. So I just fired up WSL and did like a recursive grep inside of this path right here. Program files, x86, Windows kits, 10 include, and then whatever SDK version you might have, and then KM for kernel modules, right? So the first one I was looking for was that API that Steve just showed you, the SE token get no child process restricted. And so inside of that, we see that we have a number of parameters. We have an in parameter for a pointer to the token. Now, this is an opaque structure, meaning that you can't just hit F12 on that type and see all the fields inside the header file for the structure. I think if you would hit F12 enough, it'd probably go down to a P void, right? Saying, hey, you don't really need to access this, treat it as an opaque structure. Don't mess with the structure members manually. Let the APIs do that for you, right? That's what they want. And we have a few out parameters, just pointers to some Boolean parameters to see, hey, whoever is calling this, maybe they want to know if this child process restricted is actually being enforced or not. There's also the option to say, yes, you can create a child process if it's secure. And then we have an auto only just for GWiz if you want to know what's up or not. So not fully enforced or anything like that. We're just audit mode only to see kind of what would happen. All right. So that's kind of cool to see that, to see how that API is actually prototyped or declared, if you will. So getting specific into the actual token fields, I started doing a little bit more searching inside of this. And I'm like, okay, so you said token flags, and let's see what the header file has here. All right, so some nice comments. All right, so cool. So flags that may be defined in a token flags field. All right, so if you count these up, I think we're at like 28 or 29 of these. And so maybe some of these are reserved. Okay, that'll be a little bit more to filter out. Specifically, looking at token no child process, no child process unless secure, and audit no child process. You see on the far right here these values. All right, so we have hex 80,000, hex 100,000, so on and so forth. All right, these would be what I would call in the developer speak magic numbers. Right, you never want to use magic numbers directly in your code. You want to use something like this that makes a little bit more sense when you're looking at it inside of code. So how did I go about mapping these to the specific bits that were being tested for in the program? All right, so inside of a kernel debugger, let me go ahead and break. And let's see, do I have any breakpoints set? All right, cool. No breakpoints set. So what I want to do is set a breakpoint on the API. So BP SC token get. See if I can just copy paste. Uh-oh. Don't B-side on me. And restricted. All right, so I could set a generic breakpoint there. SC token get no child process restricted. But sometimes what I like to do is figure out what the process is. So you can do DX at $cur process. Then we can also take a look at the token structure itself, doing a DX ntbang token star, and then looking at the API, how it's declared. I'm already past that point. RCX should be the pointer to the token. So if I just say at RCX, it should give me that token is being passed in for that. So hit G, go, see if I get a break here. Looks like I'm having an opposite problem that Steve was having. Too many breakpoints and I'm not getting hit with enough. Let's see. Is that a typo? There we go. Cool. So just had to kick it a little bit and create another child process or create a process. I guess my VM is a little bit slower than yours, Steve. Yours is pretty busy. All right. So we have the current process, all right, SVC host. So that is the output of DX at $cur process, right? I love the DX command. Sometimes it's great and sometimes it doesn't work the way you want it to do. All right. And then we have DX NT token looking at RCX. All right, so this is RCX. That's where that parameter is being passed into, and it's scrolled down to token flags. Token flags for this one, all right, 2A00, so we could do a dot formats. Okay, so you can see the binary representation of that hex value, and you can see what bits, if you will, what bits are set or what bits are cleared. And that will tell whoever's calling this API what mitigations are enabled or disabled. So looking at this disassembly here, Let me scroll this the other way. All right, we see the keyword pointer into the GS segment register, offset 188. What's basically happening for this piece right here is it's in the header file too. I just forget which one off the top of my head, but KE get current thread is basically a wrapper around this intrinsic function called read GS keyword. All right, so read a quad word value from the GS segment register and specify an offset. All right, so this offset right here is the K thread. So we're going to pull that and shove that into racks. So specifically looking at RCX, right? So RCX has our token, so you can kind of track where the pointer to the token is going, being moved into RBX here. We can see certain offsets, RCX plus 30. All right, so if I come back up here, look for 30. All right, so token lock, we have offset C8. See what that is, and that is our token flags. Okay, so C8, that's what we're looking for, and that's going into EDI. And then EDI is going into EAX, and then we have the shifts. All right, these shifts is what Steve was showing before, shifting right, hex 13, hex 14, and hex 15. All right, so what I did to try and validate some of those pound defines I saw in the header file, I was like, all right, so for shifting right 13, hex 13 times, let me just go ahead and do the opposite and shift left hex 13 times and see what I get. All right, so it's hex 80,000. So hex 80,000. So what you could do is go back over here and look for token flags again and look for 80,000. There it is. Token no child process. All right, so that's one that we can confirm for bit 13 or hex 13. What was that? Converting that to decimal, 16 is 3, 19. So the 19th bit or whatever. All right, so if you're following with logic, this should be 20, this should be bit 21, so on and so forth, right? So just keep incrementing and decrementing so you can map these to the individual bits that you see inside the token flags value. So if you want to validate that a little bit further, you can do 14, and you can do 15, and here we are, hex 100,000 and hex 200,000, and flipping back to the header file just for confirmation. Indeed, there it is. All right, so all of these right here relating to that specific mitigation policy of whether or not you are allowed to spawn a child process, right? And so those could be, let me flip back to debugger. Those would then be placed into certain return parameters or out parameters that we saw before, which are coming in RDX, R8, and R9. Those are the pointer to those Boolean parameters. And RDX is saying whether or not this is even enforced or not. All right, R8, what was R8 pointing to? So what kind of, let's see, token get. All right, so enforced and unless secure. So RCX, RDX, R8, R9. All right, so R14, let's see if anything is being placed inside of R14. Scroll down a little bit more. And yeah, so whatever happens to be in AL, all right, if that's set or clear, whatever that is, it's going to be shoved into wherever R14 is being stored. That way the caller can know what's happening with this specific mitigation and can go ahead and do whatever it needs to do. If you want to, you could take a look at the call stack and see some of the other APIs that may be calling some of these. SE subprocess token, initialize process security, allocate process, right? So these kind of make sense for the action that I took on my VM, where I just clicked on a link to go ahead and spawn a command prompt process. But yeah, so that was my thought process, my methodology for trying to map some of these bit fields to specific values, if you will, inside of the header files. So ntifs, ntifs.h, and around line 17,000 for those that want to check it out on their own system. All right, that's all I got, Steve.
Cool. Give me a second here. All right. So I've been fighting my system here because apparently it was delayed and stuff. Does it sound better now, Jonathan, or is it the same? Can you?
No, it's good. Okay. It's good. Yeah, you were laggy before.
Yeah, I don't know what's going on. I've got 2 access points, and both of them are acting up at the same time. So it might be my daughter on Roblox or something. I don't know. So the one thing I wanted to point out here, let me just get it together again. And I want to get your thoughts on this, Jonathan, because one thing that we were seeing is that, let me put my system back up here. Give me a second to get this one back up. Share screen. We're doing VMware. There we go. Okay, let's get this up. Cool. So my screen's back up here again, and what we saw inside that header file goes all the way up. I think the last one it was, Jonathan, was the checking the enforcement, right? To see if it's on or off. That was like the very last flag that we saw in that list. So down here, though, if I zoom in a little bit, this is the one that we ended at. But notice that this value here, this is the result. So there's audit only, and there's unless secure. So unless secure, then audit only. This isn't in that list, right? So would this be the next flag? So the after the ones that we got to at the max level? What do you think?
So is that, I'm trying to see how many zeros are after that.
There's 5 zeros. 5 zeros. Because the enforcement check was the last flag that we found, right? Or was that not the last one? Because I don't think we had this one and this one in there.
No, so I got that one. I got that one in ntifs. So that's token no child process unless secure.
Right. Okay. Cool.
And then that one right there, that 200,000. Yeah, that's audit. Audit for sure. Yep.
Yeah. Cool. Okay. Just making sure. So I guess the thought is that once we get past that point, that's it on the flags. There might be other ones in there, but I don't think we found any more. And that leaves obviously room for Microsoft to add additional flags in as they need to be put in. If we go back over here to my WinDebug session, and I think it was a K process or E process. Let's take a look real quick. WinDebug has dark mode, yes. I like to keep things bright for the screen. So let me take a look here. So if we dump out E process, this one right here is what I was talking about. So see how this mitigation flags right there, and then there's mitigation flags 2. That was a newer member added to eProcess because they ran out of space in the first one that they needed to create a second one. So I was just showing you that again because where we're at right now is there's additional fields inside the one that we were just looking at, the token flags field. But obviously, if we get past that point, they can add an additional one in. The other thing that we were looking at here in IDA, if we jump back over, was the mitigation for checking to see if you can access the Win32k syscall table. And that's why I was in this function called convert to GUI thread. And you can see down in here, as I was showing a little bit earlier, it checks the disallow win32k system calls flag, but that's not inside the token flags field. That's inside the mitigation flags field, which I thought was interesting. That I'm wondering what the determining factor as to whether or not they're going to store a flag in one field or the other is made. I'm not quite sure, but this shows you exactly how it's checking to see. Now there's going to be another flag that, or there's going to be another function that actually goes and sets that flag when appropriate. But when you go into exploit guard itself and you're turning those things on or off, that's what's telling this whether or not it needs to go and call a function to turn a flag on or leave off or put it in audit mode. We also looked last week at the event tracing for Windows and how if you select audit only mode, we'll write it to the event logs. And someone tweeted out a couple days ago when I was sending out some tweets related to this, that they took a look in the registry and saw that these flags, which makes perfect sense, that depending on what settings you make inside exploit guard is going to set some flags in the registry, which is all the brains. And then that's going to determine whether or not when you start the application up and a container gets created, whether or not that flag is going to get turned on or off. So it all ties together. And when you're thinking about bypassing some of this stuff, some of it's doable, some of it's not. So I was talking to Jonathan the other day and he was like, I just created a quick kernel driver that goes in and flips that bit to turn it off. Well, yeah, if you've got a driver vulnerability, you can potentially flip those bits when needed, but some of it's going to be too late, right? Because if the process is already created, then you're already past that point. So there's just a lot of things to consider as to how you might go around getting around some of these mitigations. Some of them might be possible, some of them not. I remember with like Emmett, for example, FireEye had discovered a long time ago that if you replay the DLL entry code and change the flag from, I think, a 1 to a 0, it basically unhooks and disables all the mitigations, even though the DLL is still there. It's just watching instead. So sometimes someone finds a bypass technique, but they're getting less and less common. And I know Offensive Security did a paper or two talking about how you can get around something specific like memprotect. A lot of them have dependencies on each other as well. Like, for example, I remember I wrote an exploit when Windows 8 came out and Dan Rosenberg did a paper talking about anti-ROP. That's what it was first called, which now is stack pivot protection. And what anti-ROP does, we looked at this one weeks ago. If you watch the webcast or stream, it actually hooks virtual alloc and virtual protect and a couple other functions. And when you go to call that function, since it's hooked, it checks to see whether or not the stack pointer points within the bounds of the thread stack as stated inside the thread environment block. So those stack limits, the stack boundaries are sitting right there inside that structure. And it checks to make sure that before you're allowed to call a critical function, that the stack pointer is pointing where it's supposed to. So Dan Rosenberg released that paper and said, well, couldn't you just pivot the stack pointer back before calling the critical function? So I wanted to see if that worked. And in a browser exploit, I actually went and got that working. It was basically the situation where I had a use after free vulnerability, and we had to use stack pivoting in the exploit in order to get to work, because I needed the push, the pop, and the ret functionality and power of those three instructions that only operate on the stack pointer. So by pivoting the stack pointer out to the heap, I was able to use a virtual function table as my array of ROP gadget pointers, and it worked beautifully. But you turn on anti-ROP or stack pivot protection, and it breaks it. And the reason it breaks it is because the stack pointer is pointing out on the heap. When we go to return, the stack pointer is pointing to the address of virtual protect on the heap, though. That's where the pointer is that we're going to return to. So anti-ROP said, wait, the stack pointer is pointing on the heap that's outside the confines of the stack. We're not going to let you continue. So I modified the exploit to basically say, well, if we get all of the arguments that we want to virtual protect. So virtual protect wants the address of where you want to change permissions. It wants because we got to get around depth. It wants the size. It wants the new permissions flag, which is hex 40, and it wants a writable address where it can write the old permissions value. And so what I did was make it so when we get the arguments ready to be written, I didn't write them onto the heap. I referenced the accumulator register because that's the register I pivoted the stack pointer with. So if I reference stack offsets relative from the accumulator register, that's going to write it to the appropriate places on the stack, the real stack. Once I got all the arguments set up, I pivoted the stack pointer back with the accumulator register. Now the stack pointer points back where it belongs. We execute the return instruction, and we bypass the anti-ROP or stack pivot protection. Well, the next problem you run into is if they turn on memprotect. Memprotect is a specific mitigation. I think it's called arbitrary code guard now. Arbitrary code guard says if the address where you're trying to change permissions in memory is within the thread stack as stated in the thread environment block, don't allow the critical function to get called, so you can't change the permissions on the stack now to make it so it's executable. So that you run into a different problem. So how can you pivot the stack pointer back, but then get it to jump over here? And like, it's always like different techniques you can do for bypasses. But when you have all of these mitigations on at once, it makes it really challenging. So looking for like these global techniques or looking for ways to get this to happen inside the kernel, but then of course they're taking away our read-write primitives all the time. Just something to keep in mind. And Jonathan had mentioned the other day, well, I wonder if PatchGuard is monitoring the specific field where we might want to change a bit. So PatchGuard, it can't check. That's another overhead example, right? Because PatchGuard, if it's validating that nothing is changed within a region of memory, how often is it going to go and do that validation? So I remember Alexander Ionescu did a demonstration of that, where you can bypass PatchGuard or defeat it and get around SMEP, which is supervisor mode execution prevention, by doing everything really quick. It's a race condition, and you better hope PatchGuard doesn't check within that short period of time. So a lot of these are race conditions as well. But like, I always get asked this question. Someone might say, well, I want to go into the world of binary exploitation, but should I even bother, or is this all going to be impossible soon? I will say this again. You've heard me say it before if you've watched me. The golden era of binary exploitation was the 1990s and the 2000s. Once we get up to like Windows 7 coming out and Emmet, that's when like mitigation started to come out of the woodwork. They're all over the place. But the question is like, is this going to be possible for much longer? Well, look at return pointer overwrites. When smashing a stack for fun profit from a left one came out in 1990 something, stack exploitation should have been dead a long time ago. The fact that you can still do it in some cases is ridiculous 25, 30 years later. So it took us that long. And now if we turn on shadow stacks and if we turn on control flow enforcement technology, which is known as the end of the death of ROP, the death of return-oriented programming, that's going to probably mitigate stack exploitation for the most part, unless someone's able to find a bypass technique that modifies the shadow stack so that you can make changes so that things look right. That's going to be the death of stack exploitation. It probably really will be. And then you look at return-oriented programming. It's called ROP because we heavily rely on the RET instruction. It's a bunch of return instructions. There is a mitigation called simulate the execution flow, simexec flow. That one does some heuristical checks to see whether or not return-oriented programming is being used or not. But if you combine that with branch checking, so there's another mitigation called, a part of control flow enforcement technology is these end branch instructions, end branch 32 and end branch 64. And the idea is that anytime the return instruction is executed, the address that you're returning to must hold a end branch instruction. It's basically a benign NOP instruction. It doesn't do anything, but it has to be there. And if the address that you're returning to doesn't hold an end branch instruction, terminate the process, because that means someone's using ROP. That is why it's seen as the death of ROP, because how many gadgets are you going to have that are usable if you have to start with an end branch instruction? So this is why the focus goes to jump-oriented programming, which jump-oriented programming is nothing new, but the purpose behind jump-oriented programming is to remove the dependency on the RET instruction by using other instructions that can still redirect the flow of execution, like a jump. So if we can jump to a gadget, we can get around the RET dependency. But there are some checks to see that too. There's string oriented programming, blind oriented programming. There's all kinds of different techniques that try and get around this cat and mouse game that we're constantly involved in, where we're putting mitigations in to try and break the techniques attackers are using. So going back to the question, will this be impossible soon? No, it won't be impossible soon. I mean, short of Microsoft rewriting the entire kernel in Rust and not using the unsafe operating like and such, I don't think it's possible for them to replace all the C++ code. If you watched like last month, I think it was, David Wiesel, I think his name is, released a little blog or even just a tweet saying, look at the first bit of Rust code. And it was like win32k.rust.sys or something else. I can't remember what it was. But it was a very small bit of code that has replaced some C++ code to do a specific thing. But to actually rewrite the hundreds of thousands or millions of lines of code all in Rust, I don't even know if that's possible. And I would imagine, too, that they run into issues where the developers behind the Rust language need to work with people like Microsoft to be able to solve challenges that come into play. Because C++ is incredibly powerful and mature. Rust is very young in comparison. So just like when H.D. Moore, a long time ago, when they wanted to move Metasploit from Perl, they were looking at both Ruby and they were looking at Python, I believe. And they chose Ruby. And the Ruby developers were actually really supportive of working with the Metasploit developers to making sure that if they hit any roadblocks, that they would modify the language accordingly and work with them. I would imagine they're in that same situation with Rust. So there are, I mean, look at the one that just came out. What's the big exploit? Somebody mentioned it last week. Is it called something jumper? Q jumper. Q jumper was that Microsoft messaging queue service thing. I went right away and started playing with that. And I know a lot of other people did as well. We've got some Discords, we were talking about it, to try and weaponize it. I saw some people trying to claim to be selling that exploit on the darknet, but you're probably not buying the real exploit. Someone's just ripping you off. But where I didn't spend enough time on it because I had work in the way. But what I was trying to do is weaponize it. And I got to the point where I found the equivalent of an RFC, which is this ridiculous 100-page document on the Microsoft queuing service or whatever it's called. It was like 100 pages of detailed documentation. And I found that someone had written a Python client that was able to actually interact and be the client server model with the Microsoft queuing service. So I was able to use a bit of that, but then had to get it implemented across a socket because I didn't want to have it just local. So you can remotely access the port. I think it's like 1801 or something was the port number. And you can interact, and was able to do the binary diff and was able to get it working to where I could crash it. And I was getting to the point where I got past just the denial of service, and I was able to get an arbitrary write within a 16-page memory region. I was hoping it was possible to get a full 64-bit arbitrary write primitive. That's not going to happen, at least I don't think. But 16 pages is pretty cool. Like I could write anywhere within the 16-page region. But I wasn't able to figure out a way yet to turn that into getting control of the instruction pointer. But I want more time. I haven't seen a proof of concept released yet. If someone's seen it, let me know because I'd love to take a look at it. But the reason I brought that up is an example of a service that was supposed to be retired now. Nobody's that service. It's antiquated, but it's still there. They left it in there for backwards compatibility support. So anytime Microsoft introduces a new attack surface, also known as a feature, that's something to go and look at. Or like I mentioned before, the folks that looked at the SIG red vulnerability, they chose a service that's interesting, that's semi-public, DNS. And they looked for the memcopy calls and they reverse engineered it. And that was a pretty easy bug, but they found it first. And it had been there since like the 1990s. So there is still a ton. There are a ton of vulnerabilities still there waiting to get discovered. The problem you run into is these damn mitigations. That's the problem. The virtualization-based security, and if we get to the point where we're running everything as an isolated user mode process, and big parts of the kernel are converted over to Rust, And in order to get to the secure kernel isolated user mode process, you got to go through some broker. They are greatly reducing the attack surface to where even if something's exploitable, what you have access to is a region. So I'll get off my soapbox here and rant, but like the short answer is no, this will not stop anytime soon. But the barrier to entrance is a lot higher than it used to be. You've got to be willing to put in the time and get all the way up to speed on all this stuff and just dive in. But it's not going anywhere. I still find stuff all the time. I know Jonathan does. I know a lot of other people that do. But weaponizing it is the challenge. So you want to say anything to do with that, Jonathan, before we wrap it up?
No, you said a lot right there, Steve. But I think in one of the comments, somebody was asking about how do malware and threat actors still have like success, if you will, with all these mitigations that we're talking about. And from my perspective, lowest hanging fruit, right? Find the weakest system on the network, go there, and then pivot around that way. I'm not going to waste my time and my energy and like my most prized tools, if you will, on the most hard box on the network, right? So I'm going for something misconfigured, going for something that's default out of the box or what have you. So my perspective, that's how they're still succeeding.
So yeah, in short, it's not going away anytime soon. Still a lot to discover and look at, but it's just harder to weaponize it. There's still a lot of people doing the patch Tuesday, exploit Wednesday. Now it's not usually Wednesday. It might be a future Wednesday, but the faster you can weaponize those one-day exploits, obviously the more valuable they are. So that's what we'll do. We'll wrap it up here with that. Appreciate everyone watching. Sorry, my audio and video was a little choppy at first. And I will figure out what we're going to look at next week. Jonathan's going to come back on, I think in August, we were looking at to show us some more advanced custom C2 stuff, which will be really fun. So I'm looking forward to that. Awesome. Alan's taking 670 with you next month. Cool. Well, thanks, everyone. We will see you next time. Appreciate it. Have a great weekend.